All right, AP Calculus. Here's an introduction lesson on 6.1, estimating with finite sums. I'm going to kind of overview and introduce what we're doing here in section 6.1. Understand this is not a replacement for you reading through the section and working through the sample problems in your textbook. It's kind of just a lesson that's supposed to give you some insight into the concepts and better your understanding after you've already read. So to start out, what we're going to be doing here is we're talking about kind of our second branch into calculus. I almost want to say that we're about halfway through here. There's two major concepts, and those would be differentiation, which we've covered, where we're looking at slopes of tangent lines and instantaneous rates of change, things like that. Well, the second branch here is called integral calculus, where what we're going to do is we're going to take a look at or investigate areas under the curves, and so in so doing, we're kind of branching out, and we're going to relate how differentiation and integration can be connected. And what we're doing there is we're actually going to be relating the slopes of tangent lines to areas under a curve, which seem like, two things that are pretty far apart, but in a little bit here you should see they're not that far apart at all. And what I've got here is an excerpt from your book here, the chapter 6 overview, and I just wanted to read this statement because it's a real powerful one here. It's these two mathematicians, Newton and Leibniz, we're talking about how they've connected these two different concepts, two geometric operations that would seem to have nothing at all to do with each other, that of finding slopes of tangent lines and finding areas under the curve. The challenge for them was to prove the connection that they knew intuitively had to be there. And the discovery of this connection, which they call the fundamental theorem of calculus, brought differential and integral calculus together. And then this is the big statement I just wanted you to see, and here's what they make, is that they brought differential and integral calculus together to become the single most powerful insight mathematicians had ever acquired for understanding how the universe worked. And it's kind of a bigger statement than what a lot of us are ready to hear or really care to even think about. But this connection opens so many doors to figuring out so many different types of problems that after you learn about it, maybe you revisit this statement and see how it's possible that they made this. So that big connection here, it's the area under the curve. So that's what integral calculus is about, is finding the area under the curve, and that area under the curve is going to basically relate to differentiation or anti-differentiation, which we visited a little bit this past chapter. Here's an example for you. Distance traveled. We know why a mathematician pondering motion problems might have been led to consider slopes of curves. But what do those same motion problems have to do with the areas under curves? Well, consider the following problem from a typical elementary school textbook. A train moves along a track at a steady rate of 75 miles per hour from 7 a.m. to 9 a.m. What is the total distance traveled by the train? Well, obviously, if it's going at this constant rate of 75 miles an hour for 2 hours, it's going to travel 150 miles. And that's just applying that distance equals rate times time. Well, you might notice that the distance traveled by the train is exactly the area of the rectangle whose base is in the time interval from 7 to 9, and whose height at each point is the value of the constant velocity function. This is no accident. Either, since the distance traveled and the area in this case are both found by multiplying the rate 75 by the change in time 2. So notice that the connection here is that the velocity um, multiplied by that change in time got to that 150 miles mark, or the position. So this is a relationship between velocity and position involving area. Well, and you know velocity is the derivative of a position function. So this same connection between distance traveled and rectangular area could be made no matter how fast the train was going or how long or short the time interval was. But, but what if the train had a velocity that varied as a function of time? So here I've got a diagram that's kind of showing this scenario. This is what I just described to you. We've got this constant velocity, and it was from 7 to 9, the times of 7 to 9, so that's a 2-hour time period. And so we found that our position was, well, 2 times 75, the area under this curve. That area that gave us the position, 150 miles away. The same concept can apply if the velocity varies. What we're going to be doing is we're basically going to be looking at, to start, the area under this curve by just considering a bunch of, that didn't work so well, a bunch of rectangles. So what we'll do is we'll take and we'll look at, if I cut this up into a bunch of rectangles, and I find the area of each of these rectangles, and you can imagine if these rectangles got smaller and smaller, the difference between them, or the difference in the height here of your velocity, would get smaller and smaller. So obviously, if we're making these rectangles, we're going to have to cut them off at some point, meaning, well, either I'll have to just use this rectangle here, or I'll go from this side and use this one, or maybe I'll cut it somewhere in the middle. And that's what we're going to be considering. Should I go from the left or the right here? How do I make a rectangle when the top is curved? And it's an approximation, basically. But you can imagine the smaller and smaller that these rectangles get, the less I'll be off in between for these areas, if that's making sense. I'll give you some better diagrams in a little bit, but that's the idea of what we're going to be covering today, is that if I can find the area of this rectangle and this rectangle, and add those all up, well, that's going to give me my distance traveled, an approximation for my distance traveled, and I get that from knowing the time and the velocity function. So I'm relating time and velocity to get distance traveled over that time. So what I'll show you here is a little bit better diagram, where this is all coming from your textbook, where you can see we split up these different rectangles. There's different ways we could split them up. And so if the strips are narrow enough, they're almost indistinguishable from rectangles. So if we made these smaller and smaller, the difference in the height at the top is almost indistinguishable, which means this rectangle approximation is going to get us pretty close. I'll show you an example of that here. So here's an example of that. It's a simple function. We've got a particle. It starts at x equals 0, moves along the x-axis with a velocity v of t equals t squared. Simple function. For time t greater than or equal to 0, asking where is the particle at t equals 3. Well, if we graph that and we and we split this into 12 subintervals, you can use the change in t to be 1/4. Where does that 1/4 come from? Well, if I am going from 0 to 3 and I want to split that up into 12 portions, 3 divided by 12 is 1/4. So each one must be 1/4 in length across, or in width, if you will. The area of each rectangle approximates the distance traveled over that 1/4 of a whatever time frame we're talking. Um, if we add all those areas up, it'll give an approximation for the total area under the curve, which would be the total distance traveled. And right here, what you can see is it's splitting up those subintervals. So you got the interval from 0 to 1/4, from 1/4 to 1/2, from 1/2 to 3/4, and so on. And then what this is showing is the midpoint. The midpoint between those would be 1/8. Between 0 and 1/4 is 1/8, 1/4 and 1/2 is 3/8, so just finding the midpoint in between. And then the height, well, that would be what you get when you plug. Remember, our function was v of t equals t squared. So if we plug in, if v of t equals t squared, well, if I plug in 1/8 into t squared, I get 1/64th, and so on and so forth. So that's showing the height of the rectangle, or at that midpoint, and then the area would be the product of those two. So what this is showing, if we jump back to this previous diagram, is what we're doing is if we just looked at this one rectangle right here, what we're doing is we're looking at, okay, I'm finding the value right in the middle, I'm finding how tall it is there, and I'm going to consider that rectangle. So in that case, it would go about that high, and we're looking at this rectangle right here, and we're saying, okay, this portion underneath the curve has this area, doing that again for all these 12 portions, adding them up to get the approximate area underneath that curve. So if you continue in that matter for all of the subintervals, you would simply add up all those areas, and you get approximately 8.98. There's different methods. There's a there's the left rectangle approximation method, the middle rectangle approximation method, and the right. So what that does is, I always use left hand, right, middle, and right hand. What that's doing is basically, this is the curve here. What you're doing is, if it's a left hand, you're going up just as high as the left part of the rectangle hits, and then taking the area under that. You can see how we're missing all this space in here. Use a little marker here. We're missing all that. Well, we're missing this here, we're missing this here, we're missing this here, we're missing this here. So obviously this is going to be an under approximation. If we go over to the right-hand method, well, now we've got extra here, extra here, extra here, extra here. That's going to be an over approximation. And then here, we use the midpoint, and that's what was described earlier, where, okay, now we went over a little here, we're under a little right there, or we're missing a little bit there. Here we've got extra rectangle, here we've got less, and so this is closest, is what I would say in this particular curve. Well, if we keep going with that, to get the estimate under the graph, oh, that went too far. These are just different approximation methods. And that's really what I wanted to show you, as far as what it is you need to know, kind of going into reading this section and getting your information. Miss Robley is going to come in and give you some programs, or show you how to copy programs that I have on my graphing calculator that's going to allow you to split the areas under the curve into many more rectangles than what you have. So, like for instance, if I have this graph here, x squared sine x from 0 to 0 equals, or x equals 0 to x equals 3, what I'm going to do is you're going to apply this RAM program that, again, I'm going to download, or you're going to be able to share with it between your calculators, where you can have that add up 1,000 subintervals, which would take you a little while to do, and find approximations that way. Now understand, you're going to have to be able to do it this way, where you find the midpoint, you find the area for each interval, add the intervals up, and you need to be able to do it that way. But we also want to be able to we also want to be able to do it this way. So when we have that program, we can add those different things up. Um, so just kind of showing you different examples. If we had um, that y equals x squared, this just shows you how to connect or how closely connected the different answers are. Where if you use the LRAM, left-hand rectangle approximation method, I told you it was an underestimate. It says the area would be about 6.875. I thought the middle one was closest, and I thought the right-hand one was an overestimate at 11.375. And that middle one was 8.9375, and so on. So as we can see from there, the smaller one, the left one is smaller than true, the right one is larger. That's what I just talked about. Um, but the more subintervals you have, the more accurate it's going to be. So I think with that said, Ms. Robley should be in shortly to give you that program. Again, I just wanted to give you a little bit of a little insight into what you should be reading about and what you're going to apply. We'll talk about it again Monday. You'll get your tests back hopefully on Monday or Tuesday. And then I was hoping to introduce 6.2 before the break. I'll give you a review packet before the break for the final, and that's our plan. As you can probably see down here in the corner, it's about 11:15 at night here. We got back from our Menominee duel last night. We beat them. Uh, they were ranked second in the state, so that's kind of a big win tonight. But I thought I'd better get in here and give you a little intro. For now, I'm going to go home and see my family. So, take some good notes, practice up, bring some questions on Monday. Hope you have a good weekend.